Seems like really light attendance today. Alright, good morning. I've heard there's a cold going around campus, and I'm pretty sure I've got it, so try not to make me yell too much today. Also, if you have it, come help yourself to a cough drop. Let's see. It was Saturday night. It was 9 o'clock, and my wife and I had eaten dinner, and I was already like in my pajamas. I don't care, judge me all you want. That's how I spend my Saturday night, and or at least this one. So we hadn't eaten, and so what do you do in that situation? Pizza's a common one. One of our go-tos is the Chipotle run, and so I thought, yeah, let's just do it. Let's go to Chipotle, and so I threw on my Crocs. So I'm wearing pajama pants, like with big blue bows on them, and a t-shirt that's like a 2X. It's like down to my knees almost. And my poor wife. Anyway, and so then I'm wearing Crocs, and so I don't really think much about this. But of course, I walk into Chipotle, and immediately there are like 5 students. And I look ridiculous. So lesson learned. I should at least like put on some pants or something going forward. All right, when is the exam? Tuesday. Man, we are close. We've got 1 week of class left. I actually looked back. I was like, today the perfect song would be 1 week, but that was used up like a month ago. And so I googled week and then weekend. I love the song Weekend Horse, and so we just did that. Close enough. So the exam is Tuesday. What was I going to say? We have one more homework due that is due when? Wednesday of this week. So make sure you get that in, and then let's see. So then the exams are very close to being finished grading-wise. I think they're going to come in a little lower than the other exams. I might have slightly missed the mark on those. Is that going to affect the grade distribution at all? No. I'd tell you day one that if things are low, I'll curve as necessary, and so that is going to happen. And so that's not going to have a big impact on grade distribution whatsoever. So not a big deal. I should get those back to you on Wednesday, and then we have Friday. 10 o'clock asked, and so you might be wondering. So Friday, I've been here on the last day of classes. I've been like passed out by 1 p.m. on the last day of classes before. It's embarrassing stories. I could go into more detail, but not necessary. And so we are going to have material on that day. It's going to happen. We're going to have some new stuff. It's largely going to be review, but there will be some new stuff, and I just want you all are cognizant of this, but I post my notes, and I put a podcast, and so, if you're not 100%, just 100% on Friday, just check it out on Saturday. You got the weekend, so I get it. All right, I think that's it. So let's get rolling. I might let you go a little early today. So here's the thing. Have you guys been getting a lot of eval emails and things? Aren't those great? So here's the thing. 10 a.m., my eval completion rate is about 38%. 11 a.m., here's the thing, though. They know that now. I gave them these numbers as well, and so I have a feeling, and in fact, I let them go early with the promise that that time that I gave them, they would give back to me today. And so I'm guessing that number is going to shoot up quite a bit. So we'll update as we go. In 103 last semester, I got 80% on my evals. I'd love to get up around there. And the whole spiel about evals being taken seriously, they are. I read those very closely, and they mean a lot. So, yeah. If you beat them, tell you what, whoever is leading as of Friday morning gets a better explosion on Friday. So that's what I can offer. I can blow some stuff up. So you get the better explosion. It's on the line. It's in your hands now. Okay. All right, so let's get into it. So we talked about regiochemistry of E2 mechanisms last time. And so today we're going to further our conversation about E2. And so specifically, we're going to start talking about stereoselectivity. All right, so one special thing about the stereoselectivity of E2 reactions is that the beta hydride is being eliminated. It has to be able to take, seriously, my throat is sore, so just help me out a little. So it requires that the beta hydride be anti-coplanar, and so what that means is it's most easily seen in a Newman projection, but in a Newman it's got to be in the same plane, right? But it's got to be on the other side. It's got to be 180 degrees to our leaving group, and that's going to have an impact on the stereochemical outcomes of our reactions. So, for example, what we can take a look at is, let's see, we'll start with this product. And so we'll put a methyl on a dash, hydrogen wedge. All right, so we've got something we can do here. And so what we're going to do is we're going to treat it with, say, sodium methoxide. Now let's think about that for a second. All right, so we always want to see if we can do SN2 or E2. And so what kind of alkyl halide do we have here? It's a secondary, right? So we've got a secondary alkyl halide, and so we can do SN2, we can do E2. And so then we want to look at the nucleophile slash base. And so in this case, it's sodium methoxide. Now, is sodium methoxide a good nucleophile?
Yes.
It is. Is it a good base? Well, let's think about that for a second. So, of course, when we have secondary alkyl halides, we have to think about the pKa of the conjugate. So what is, again, the conjugate of methoxide? Methanol, and so methanol has a pKa of about 17. So that comes in above that line of 11, and so is this going to go through an E2 or an SN2? Definitely an E2, right? So if it's above 11, that makes it a strong base, and we're going to favor elimination pathways. If it's under 11, it's going to be a weak base, and we'll favor SN2 pathways. All right, so if we take a look at our substrate as drawn, we're going to end up with a Newman projection. And so let's see, we've got our bromine in the back, our hydrogen in the front. So it looks something like that. Here we've got hydrogen, methyl, and then methyl. Okay, so here's the conformation that we've drawn. Now in this case, we have a beta hydride, right? And so here is our beta position. And so we do have a beta hydride, it's that right there. And so our beta hydride circled down here, of course, is that one right there. But then our leaving group right here is our bromine. Now are they anti-coplanar to each other? They're not. So what that means is that in this conformation, we're not going to be able to do any sort of E2 reaction. We're first going to have to do what? Can we make it such that the hydrogen is anti-coplanar? Yeah, we absolutely can. And so what we'll do is a bond rotation. And so if we rotate the left side 180 degrees, really just got to rotate one side, but we'll rotate the left side 180 degrees. So that's going to put our hydrogen on top. And so for this left carbon, the methyl, which was on a dash, is now going to be on what? It'll be wedged now, right? So it's flipped 180 degrees, as well as the ethyl, which was on a wedge, will now be on a dash. And so the right side will stay the same. So we've got our bromine down, methyl on a dash, and hydrogen on a wedge. And so now do we have an anti-coplanar beta hydride to our leaving group? Yeah, we do. And so for proof, we'll again draw another Newman. And so in this case, our Newman will be a little bigger. In this case, our Newman projection, we have our hydrogen in the front, methyl to the bottom right, ethyl to the bottom left, bromine, hydrogen, and methyl. And so what we've got now is our hydrogen and our bromine are, in fact, anti-coplanar. So now that we've got them in that anti-coplanar conformation, we're able to go ahead with our E2 mechanism. And so in our E2 mechanism, we're reacting it with methoxide, which is a strong base. And so we will deprotonate while forming our double bond and kicking off our leaving group. Okay, so everything on a wedge is going to stay on a wedge, and everything on a dash is going to stay on a dash. And so that's going to lead to one stereochemical outcome. All right, so we're forming a pi bond. And so on the right side, we've got our methyl on a dash, and we've got our hydrogen on a wedge. On the left side, we've got our ethyl on a dash, and our methyl on a wedge. And so which product is that? Stereochemically. So we'd say priorities are 1, 2, 1, 2. And so is that E or Z? Yeah, that is definitely going to be Z. And so in this case, because of that requirement that we have our beta hydride anticoplanar, what we're only going to see formed is the Z product. And that's because we have to be in this conformation. The other conformation that I'd shown is never going to be able to do an E2 elimination. Okay, so that's in an acyclic system. This also has a pretty big impact on a cyclic system. And so in this case, we'll look at a relatively simple fluorocyclohexane. And we'll think about doing E2 elimination on this. So we'll hit it with the same thing. We'll treat it with sodium methoxide. And so as a strong base with a secondary alkyl halide, we're going to favor an E2 mechanism in this. But we have to go one step further whenever we have cyclic systems. And so, I don't know, do chairs bring back good memories or bad memories for you guys? We'll call it a mixed bag. And so this is actually a pretty good review. What are the odds you'll probably have to draw some sort of chair on the final? Probably pretty high, so yeah. Yeah. All right, so this is going to ultimately be a pretty solid review. Is that good? Okay. All right, so this will be a pretty solid review for the exam anyway. And so what we're going to have to do when we have a cyclic system, and we're only going to look at cyclohexanes. That's the easiest one and the most common. We must consider chair conformations. All right, so this is good. This is actually a really good exam review. So if we draw one of the chair conformations, can I go down now? Yeah. Okay. All right, so one of the chair conformations we'll draw like this. And so again, I think it's a really, really good bookkeeping tool to number your carbons. That way you don't lose track of anything. So in this case, we'll say 1, 2, 3, 4, 5, 6. And this isn't the IUPAC naming of the, this is just we're assigning some numbers so that we don't get lost when we're going from conformation to conformation. Okay, so in this case, we've got our chlorine on what we're calling 2. And so we'll go ahead and put this in the equatorial position. And so we have one alpha proton, which is going to be axial there. Are we ever going to do any reactivity with the alpha proton? No, we're only talking about beta elimination. So this alpha proton is just going to be there to help us keep track of our conformation. So we do want to show in draw in our beta hydrogens. So we'll have this carbon number 3 with a couple. And then we'll have carbon number 1 with a couple. Okay, so the requirement to do an E2 elimination, you have to have anticoplanar beta hydrides, or beta hydrogens. And so in this case, our beta position is 1 and 3. Now let's think about what that anticoplanar really means. So that means if our chlorine is, say, straight out to your right, we're going to have a beta hydrogen, which is straight out to your left. They have to be anti, right? They have to be 180 degrees from each other. And so when we look at this picture, so we've got our chlorine equatorially kind of going out this way. Do we have any beta hydrogens that are anticoplanar? Definitely not, right? So here, the axial hydrogens, well, those clearly are not 180 degrees, right? They're going straight down while our leaving group is going this way. And then equatorially, we're going to have one chlorine going this way and then the hydrogen going this way, or the other one basically doing the same thing. And so what we're finding is when our leaving group is equatorial, we're not going to be able to undergo any beta hydride elimination. So we can say that in this case, there are no anticoplanar beta H's. And so because there are no anticoplanar beta H's, and because that's a requirement of an E2 reaction, well, there's just simply going to be no E2 that can take place with this chair conformation. Okay, now, is this the only conformation that this cyclohexane exists in? No, it's not. And so what we want to make sure we show is this thing is, of course, in equilibrium with the other chair. And so the other chair, we flip our headrest and our footrest. And so we'll number so that we can keep track. So now this is 1, 2, 3, 4, 5, 6. And so our chlorine, which was initially equatorial, is now going to be what? It'll now be axial. And so again, we'll draw in our beta hydrides. And so in this case, now we've got our chlorine straight down. So we look at our beta hydrogens. Do we have any that are straight up, satisfying that anticoplanar requirement? Yeah, absolutely. In fact, we've got multiple options, right? We've got that one, and then we've got that one as well. So now we find that we've got two anticoplanar beta hydrogens. And so E2 is going to be very much possible. Now in this case, let's see, we could eliminate the beta hydrogen on carbon 1, and so that would lead to this product, or we could beta eliminate the hydrogen on carbon 3, and so that would be, not that one, but that product. Well, what's the relationship between these two? Yeah, those are the same. So here we've got ultimately the same product. So we're only going to have one, but here's the key thing is we're going to have, here's how we want to do this. First off, you expect that we do have E2 conditions, but we can't just assume that we can form this product. What we have to do is draw out the pair conformation and make sure that conformationally now the E2 is possible. So in these cyclic systems, we have an additional responsibility. We have to make sure that conformationally it's possible. In this case, in a lot of these mono-substituted cyclohexanes, clearly it's not going to be a problem, right? Because we're always going to be able to form this chair conformation and go forward. But when we look at more complex cases, as the one we're about to do, so let's throw a methyl group on there, and let's see how that impacts things. All right, so now we'll still do a chlorocyclohexane. So we'll put our chlorine down here, and since we've got different substituents, we've now got stereochemistry. And so now we're going to have a methyl there. So we've got a chlorine at the bottom on a wedge and a methyl on a dash. So we'll treat it with the same condition. So again, we'll go sodium ethoxide, which indicates that we'll likely be looking at an E2 reaction, if at all possible. Okay, so let's think about our chair conformations. So let's see. All right, we'll just number from the top. 1, 2, 3, 4, 5, 6. So here we'll go 1, 2, 3, 4, 5, 6. And so that means that our methyl on carbon 2, is that going to be axial or equatorial? Remember, when we're looking at the ring right here, really what we're doing is kind of looking down on it like that. And so in that case, is the methyl coming towards us or away from us? Away from us, right? So we've got two options for carbon 2. Which one's coming away from our eyeball there? The equatorial, right? All right, so it's the one that's further away from our eyeball is going to be the methyl. And so likewise, on carbon 3, we have the chlorine coming towards our eyeball. And so is that going to be equatorial or axial? Equatorial again. All right, so then we'll draw in our hydrogens on 4. And so when we look at this chair conformation, all right, do we have beta hydrogens? Yeah, absolutely. We've got 3 beta hydrogens, right? But how many anticoplanar beta hydrogens do we have? We don't have any. And so what we're finding is that to be able to do an E2 reaction on a cyclohexane like this, again, the leaving group essentially has to be axial. And so let's see what happens when we draw the other chair conformation. All right, so flip our headrest and footrest. And so we've got, let's see, 3, 2, 1, 4, 5, 6. Okay, so we've got our hydrogen on 2, which is now equatorial. On methyl, on 3, our chlorine has been flipped up to axial. All right, so we still have 3 beta hydrogens. But when we look at this chair conformation, do we have any anticoplanar? Yeah, how many do we have? We just have 1. And so what we're seeing is by having this methyl group next to it, essentially we're never going to be able to eliminate such that we form our pi bond between carbons 2 and 3, right? Because we're never going to have an anticoplanar beta hydrogen at carbon number 2. The only option, the only thing we ever see is this 1 anticoplanar hydrogen right there on carbon number 4. And so in this case, we only have 1 anticoplanar beta hydrogen. And so what that means is only 1 product will form. All right, so if we do eliminate that hydrogen on carbon number 4, we're going to form a pi bond between 3 and 4, and so that's going to lead us to this product right here. And so remember, that's 1, 2, 3, 4, 5, 6. Would any other product be possible if we hadn't done this chair analysis? All right, so just looking at this picture, we do have a beta hydrogen on carbon number 2, right? And so without doing the chair analysis, we could have looked at that and thought, well, there's no reason that we won't be able to form this product. But so what we're finding is that after doing the chair analysis, this one is not possible due to lack of anticoplanar beta hydrogen on carbon 2. So we just never have that conformation that's necessary for us to be able to form this product. So the only product that we would see form would be this one. Does that make sense? It's pretty relatively straightforward. And so that we basically need an extra line of thinking from now on. So anytime you see a cyclic system and you're going to try to do E2, we just have to make sure that conformationally we end up having a beta hydrogen that will end up leading to that product. All right. So that's that. We'll skip ahead now to Roman numeral number 3. And this should help out quite a bit with the homework. I think there's a lot of, or at least several cyclic E2s on the Sapling homework this week. So this will be the stepwise mechanism. And just like we called the stepwise mechanism in nucleophilic substitution the SN2, what are we going to call it in elimination? I'm sorry, stepwise in nucleophilic substitution was SN1, and so stepwise in elimination will also be E1. Going backwards. All right, so E1. And so what we'll start off with as letter A is going to be kinetics. And so the first thing that I'll say is that like SN1, E1 proceeds through a carbocation. So there's actually going to be a lot of similarities between these two. All right, so let's see what's going on. So if we draw an example, let's say we have this tert butyl bromide. And so we'll react it with H2O. Okay, so what kind of alkyl halide is this? Yeah, it's a tertiary alkyl halide. So are we ever going to be able to do SN2? No, there's no SN2 possible. Are we ever going to be able to do E2 with the conditions shown? Do we have a strong base? No, and so of course the conjugate of water is hydronium, right? And so hydronium has its pKa of around -1.7, and so that's clearly a pretty strong acid, and so we're not going to be able to do either SN2 or E2. So this says no SN2, and then this says no E2. So we're basically stuck thinking carbocation pathways at this point. So let's do that. Let's see what happens. So the first step of a carbocation mechanism, of course, is going to be the spontaneous leaving of that bromine. So what we're going to form is this tertiary carbocation. Is that a pretty stable carbocation? Yeah, and so what we're going to find is these we've already seen that SN1 can only take place at tertiary and secondary alkyl halides, and the same is true for the E1 mechanism. It's going to be tertiary or secondary, otherwise it's just not a stable enough carbocation. All right, so we've still got our water in solution here, and so we've got our H2O with its lone pairs. And so when we look at this carbocation, do we have any beta hydrogens? Yes. Yeah, and so when we talk about the alpha position has basically become the carbocation, right? It is where the leaving group was connected. It doesn't change. It's still the alpha position. And so, in fact, in this case, we have a lot of possibilities for a beta hydrogen. And so our beta carbon would be right there next to the carbocation. So we do have a beta hydrogen. So we are definitely going to be able to undergo an E1 reaction or an elimination. Now, again, is water a strong base? It's not a strong base. Why is that not really going to matter? That carbocation, how stable is it? It's pretty unstable. Now, in terms of carbocations, it's stable, right? It's a stable carbocation. But compared to a completely full shell molecule, how stable is it? It's very unstable. It's going to be very reactive. So we no longer need a strong base. So once we've formed our carbocation, we've got a very, very reactive carbocation that's going to do anything possible to become not a carbocation. And so it will react in an acid-base reaction with a weak base. So what we'll see happen, let's change this color to blue. So what we'll see in this reaction is this as follows, and so we'll do our elimination. What we'll end up with is this product right here that has proceeded through an E1 type mechanism. But that is not all that's going to happen. And so with these sets of conditions, what other type of reaction that we know could also take place? We could also, instead of attacking that beta hydrogen, attack directly the carbocation. And so then after a deprotonation step, we would end up with this alcohol. And so what kind of reaction is that? That is an SN1. And so what we're going to find, and so what we'll say down here, we'll star it. That is the ugliest star. We will star it, and we will write keynote. All right, so if we have a reaction that goes through a carbocation, we'll say that a carbocation mechanism, pretty much always, can we say always? We can't say always, but we'll say almost always, leads to both an E1 and SN1 reaction. And so they both are going to take place. Anytime we go through a carbocation, if we're able to do an elimination and a substitution, we're going to do both. I'm never going to look at you and say, all right, you've got some conditions. Is E1 going to be favored over SN1 or vice versa? It's just too hard to tell. Once you've got a carbocation, the carbocation is just going to react any way possible, and so we can end up with a multitude of products. Now, they aren't always possible, and the reason I threw in this almost always is, say, with what if we don't have a beta hydride? Are we going to be able to do elimination in that case? No, and so in those cases, we might only see SN1, but it's going to be structurally, it's going to be dependent, right? If we don't have the beta hydrogen to eliminate, that's going to be the only case that we don't see the elimination. All right, so if we can do both E1 and SN1, we absolutely will see both products occur, and we end up with a pretty big mess on our hands, to be honest. All right, so what's the rate determining step in this reaction? Yeah, it's definitely the first one, right? It's going to be the formation of that high-energy carbocation. So what we can say is the rate is going to be equal to a rate constant times our alkyl halide. And so again, we can see that this is unimolecular, just like SN1. And so that leads to our E1 naming. All right, is that the same rate law as with an SN1 reaction? Yeah, and so they basically are going to proceed at the same rate, and that's why we always see a mixture of products. All right, so we don't have as much to say about this one, so we'll just talk about regiochemistry for a few minutes. And so fortunately, we'll talk two things. So first off, we'll say that an E1 reaction is going to follow Zaitsev's rule. You guys remember Zaitsev's rule? Yeah, and so, yeah, the more substituted alkene is more favored. So that's pretty easy. That's just like with an E2 reaction. We find that we're going to favor the more substituted alkene. And so as a reminder of that, let's say we've got this substrate. And so we're going to react it with methanol. And so we see that we've got a secondary alkyl halide. We have no strong nucleophile, so no SN2 is possible. We have a weak base, so no E2 is possible. And so the only thing that can happen is we form a carbocation. All right, so the possibilities for beta hydride elimination. So we have a beta hydride here, and we also have a beta hydride here. So we've basically got two possible beta hydrogens which we could imagine eliminating. So that's going to lead to a red product that looks like this, plus a blue product that looks like that. All right, so two possibilities. We can eliminate to either side of our leaving group. And so which is going to be favored? Which is the Zaitsev product, red or blue? Yeah, it's red, right? Because it's tri-substituted over a mono-substituted alkene here. And so the red one is our Zaitsev product. And so which one is our major product? It's the Zaitsev. It's always going to be the Zaitsev. So here's our major, which means our blue one is going to be our minor. All right, so that's pretty straightforward. That's a lot like E2. We're just going to follow Zaitsev's rule. So then the second part of this is that, let's remind ourselves, we're going through a carbocation mechanism, and so a lot of things can happen. What's the final complicating thing that we haven't really discussed yet? Shifts, right? And so, because we're going through a carbocation, shifts are possible. All right, so for example, you could be given something such as this. All right, so again, we're ignoring any stereochemistry in these things for right now. So let's say that you react this in methanol, and so you end up with a product that looks like this. All right, and so, there we go. Let's make it prettier. There. All right, so we have that product there. We have a tetra-substituted alkene. And so it's not totally obvious how we can get to that tetra-substituted alkene from this, but if you're ever stuck on a mechanism, I've said this several times, think about what kind of mechanism we would go through and just do the first step. All right, so we can't do SN2, and we can't do, and in fact, we're seeing that the product's elimination, so we're definitely doing either an E1 or an E2. Now, do we have a strong base that can do an E2? Is methanol a strong base? It's not, right? And so we're going to try an E1 mechanism, so the first step is what? Yeah, the leaving group leaves. And so let's just do the first step, and then we'll think about what we can do from there. Always a good idea to just do what you know. And so in this case, what we're going to end up with is a secondary carbocation there. Now, are we going to be able to form a more stable carbocation? Yeah, what are we going to do? Yeah, so in this case, we're going to do a 1,2 methyl shift. And so in our 1,2 methyl shift, we'll take one of these neighboring methyl groups, we'll shift it onto that secondary carbocation. And so what we end up with is going to be this tertiary carbocation. Is there a good thermodynamic reason for this to happen? Yeah, all right, so we're going from secondary to tertiary. What else is going to make this an incredibly stable carbocation? Yeah, there's resonance, right? So this pi bond right here can resonate over to this position, and so we can also resonate the positive charge around the ring. So it's going to be a very, 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 very stable carbocation. And so from here, do we have a beta hydrogen that can lead to our final product? What about right there? So what we could do, deprotonate, just like that, and that should lead us right back to our final product that we were trying to get to. So, shifts can take place. Overall, this stuff, carbocations, right? Messy, just a lot of possibilities. Okay, so that'll be regiochemistry. The last part we're going to talk about is going to be stereochemistry. And so what was our stereochemical requirement when we did E2? Yes, anti-coplanar. And so what we're going to find is when we do an E1 reaction, we'll say that anti-coplanar beta hydrogen is not necessary. So we no longer have that being a requirement. And so what that means is that both E and Z alkenes will be possible. So let's think about mechanistically really why that is. All right, so let's say we start with this, and so we'll show that beta hydrogen syn coplanar because it's not going to matter. And it doesn't matter because the first step of this reaction doesn't even involve the beta hydrogen, right? So where the beta hydrogen is, it's not going to make a difference whatsoever. So the first step, of course, in an E1, we'll just say E1, is that our leaving group will leave. And so what we end up with is nothing's going to change on the left side because we're not doing any chemistry there. So our methyl and our ethyl and our hydrogen are still going to be in the same situation. All right, so on the right side, though, we're going to have formed an open p orbital. And so since a carbocation has what kind of hybridization? It's sp2, it's going to be trigonal planar here. So we draw our trigonal planar geometry. And so what you're seeing now is we have this open p orbital, right? So we've got a positive charge on the carbon. And so that positive charge derives from the fact that we have an open p orbital where there are no electrons. Now, of course, a p orbital has two lobes, right? And so the only requirement is going to be that the electrons that end up forming our pi bond, they want to be in the same plane as our p orbitals. And so when we look at this bottom lobe, are these electrons in the same plane as this lobe of the p orbital? Yeah, absolutely it is. And so what we can do, we can go over here and we'll go around. We will deprotonate such that we form our pi bond. And so we're going to form an alkene where we have ethyl and methyl. And then the same thing. And so basically our wedges stay the same, our dashes stay the same. What's the stereochemistry of this alkene? Yeah, it's going to be Z, right? So the ethyls are our higher priority groups. And so we've got 1, 2, 1, 2. So that is absolutely the Z alkene. But since we go through that carbocation intermediate, what could happen as well is we could undergo some form of bond rotation. And if we undergo that bond rotation, we could say, well, now we've got a hydrogen straight up. And so in that case, the methyl that was on a wedge is now on what? It's now dashed, and so our ethyl is now on a wedge. Our carbocation will stay the same. And so if we deprotonate the beta hydrogen now, well, is it going to be in the same plane as this top lobe of the p orbital? Yeah, again, they're just both in the plane of the board, right? And so again, what we're able to do is our beta hydride elimination. This case, though, we're going to get different stereochemistry. And so now on the left side, our methyl is on a dash, where our ethyl is on a wedge. And then the right side will ultimately stay the same. We didn't do anything. And so what's the stereochemistry of that alkene? Yeah, so now we've got E. So we see now that because we go through that carbocation intermediate, well, the hydrogen never has to be anti-coplanar, it just has to be coplanar, right? And so there's two possibilities. It can be coplanar with the lobe on the top, or it can be coplanar with the lobe on the bottom. And so that leads to both possible stereochemical outcomes. Okay, so to summarize, what we will say is that this only, let's clarify, we'll say that E1 only occurs at what kind of alkyl halides?
Secondary.
Yeah, secondary and tertiary, and that's because those are the only stable carbocations that can form. So we'll only see E1 as secondary and tertiary. And then finally, just like an SN1 reaction, it is messy, and it's messy because we always see SN1 along with E1 products. And of course, we say a slight caveat if possible, because there are cases where we don't have beta hydrogens and thus can't do an elimination. All right, so that brings us to the end of E1. What we're going to do next time is we're going to put together a really nice and neat flow chart, because we've got a lot of things going on. We've got SN1, SN2, E1, E2, and we've seen differences depending on if it's a methyl, a primary, a secondary, or a tertiary alkyl halide. So we're going to put together a nice, neat flow chart that should be really, really helpful going forward with the final. You guys are getting a lot of time today, so I'm giving you 10 minutes. And so like I said, this 10 minutes is specifically meant to be 10 minutes for you, and it should only take like 2 minutes to fill out an eval. It shouldn't take very long. Sometime today, remember that whatever you're doing, you got an extra 10 minutes today, and I'd highly appreciate it if you fill out that eval. Yeah, there's stuff over here. If it's anti, we're able to form the pi bonds with what is an antibody. But on this side, if we were to try to eliminate, well, there's just stuff here already. And so we have to have all this to be
This is planar. This one was anti-planar. Yeah. So